Yeah, all good? Yeah, oh, yeah. So thank you everyone to come today. And before we start this very interesting topic, I want to understand how many data scientists we have, because like if we have less than 2, I will need to go. Okay, we have 3, 4, 5, okay. Whoever not data scientists, please raise your hand, because otherwise I will have to go. We need at least half. Okay, cool, yeah, we got one. So basically, data scientists are the people who run data science projects, obviously, right? But this topic, the set of topics I will present in my presentation will be interesting for the wide audience, for like data engineering people, for people who work with data, data analysts, and so on and so forth. But the reason why it's called essential data engineering for data scientists is because like during execution of many projects we run in SoftServe related to big data, to data science, we came to very interesting conclusions that I will explain later, right? But before we start, a couple words about myself. So because I will need to build this trust, you see me for the first time, how can you trust the person you see the first time, right? So I will just give you a couple of the ideas why you need to trust me. Is 15 years working with databases. I worked with databases like, who remember the database called Fox Pro? Oh, Jesus, I'm not that. Okay, cool, great. So 5 last year I spent like working with big data, with like Hadoop and stuff like that. Who heard about the Hadoop? Excellent, excellent, we're getting there. And eventually I started leading the big data practice at SoftServe, and also founded a couple of communities. One of them is like big data community in Kyiv, in my like native city, where we have more than 600 people attending very similar meetups. And I'm very glad I can like share it, like experience we have with you guys here, right? And some of the agenda on the topics we will be covering, right? On the screen, I will not read it, this slide, just take a look on it quickly, and let's go. So basically, the reason why I mentioned the projects we do is like I have like statistics based on about like 20 projects we did so far, and not all of them were successful, like a couple of them were not successful. And we try to understand like where is the level of like measure between successful project, not successful project. And on data science, like the success of the project depends on will data science people really get this value out of data, right? Because even when you have right data, right tools, right clusters, if data scientist is not capable to write the right model, get the value out of it, it's all not successful, right? But even before we get to the data science modeling, which is number 6 in CRISP-DM model, who knows CRISP-DM model for data scientists? Okay, cool, great. Even before we get to this level of like modeling data, right? There are a couple of steps we need to go through to actually prepare this data, to get it available to data scientists, right? So that he or she can start work with this data. And our statistics shows that more than 90% of failed projects is actually fails even before data science guy get this data. Just because like data engineering people were not able to provide data scientists with the data, or were not able to provide him with the performance he needs to run the algorithms on top of this data, and so on and so forth, right? So that's why in our practice, we started involving data scientists into the designing of the system from the very beginning, from the requirements gathering, from the picking up right tools, from the setting up clusters and making data available actually, right? Because what? Because if these other guys, data engineers, will not be able to be successful, he or she will not be able to be successful as well, right? It's as simple as that. And at the end of each section, I will have the checklist, right? This is the like very short list of things from this, let's say, call it chapter, right? So very quick checklist from this area is that data science person is a boss on a project. He's the person who is actually getting data out of value out of data. But if he don't have this data, he will not be able to go further. And to be able to influence on the solution, he needs to start from the very beginning. But when you start talking to the big data, like people, data engineers, you need to have good argumentation to prove that like they are like right or wrong, right? Okay, let's go. So choosing right tools. Why it is important? Like I will tell you a very short story from my history. Like, I've been visiting one of our customers in Texas, in Austin, and I came to the like rental office to get a car, and they like giving me keys. I go to check the car, and in fact, the car was like this. Oh, let me show you. And I'm like, why this car? It's like, we don't have any other cars. I'm okay, and what? And like, you either take this car or you don't have car at all. I'm okay, I take this car. So I had to go to the customer on this car. This was actually 12 seats van. It's huge. It's enormous. You're like like there were two entrances to this parking, and one of them was too like small. I was not able to fit inside, so I had to find another entry, and then I was able to park. And you see the tail of this car. It's like pedestrian lane is almost like blocked because like no other options. Hopefully in Texas, like all the parking slots are big enough. In London, I will be probably like stopped, right? There is no parking like in Texas here. So, and the same happens in big data world actually. Like everyone see this picture on the screen, like many saw this before. This is like a list of big data technologies. And these days, who will guess the number of big data technologies in hundreds? 8. A little bit less, like it's 500 technologies at the market. So you can imagine like, let's say data engineering team who have to decide which of these 500 technologies are right tools for you, right? And if you will not be able to influence on it, then you'll probably get the same car as I got, right? And you will have to drive it one way or another. And so the question, how to pick up the right tool from this list. And the key for this, to answer this question is called reference architectures. So in many cases, in most cases, for the problem you're going to solve, somebody already solved this similar problem, and in most cases, he or she created the reference architecture, which will show you like what type of tools do you need to pick up. In many cases, it gives the example of tools you need to pick up, and you need to decide like between couple tools. So this 500s converts into the like 3 or 4 tools. You need to decide which one is the best for you. And once you get to this, like for instance, if you need to decide which version of Hadoop you need, right? There are like several main players on the market, like Cloudera, MapR, Hortonworks, and there are like tons of comparison metrics between these tools. So like even if you're not a like big data guru, data engineering guru, you can easily go and check what's the benefit of Cloudera, and you can find out tons of articles saying that Cloudera is very good in retrieving data fast because they have this like Impala tool, let's say, yeah. Or if you're looking for grab data from many different data sources, then you're probably good to go with Hortonworks because it has built-in tail-and-D tool. It comes free of charge, right? And so on and so forth. So as a data science person, as a data analyst, you can actually at least validate the architecture solution which big data people like provide to you, right? But it's not like only like black and white, like only like Hortonworks, Cloudera. There are many more new players on the market, including like IBM, who has a brilliant like products called Big R and Big SQL. Big R is actually what's interesting about Big R. Who is familiar with Big R apart from the IBM guys? Yeah, you see, and if you're not familiar with it, like you will never be able to validate the architecture you've been given, right? But Big R is the set of data science algorithms, which IBM has a lot. So they have a history of like many years written these algorithms. So what they did, they converted it into set of libraries, into set of like libraries you can use in Spark, in Hadoop, everywhere, like ready to use, right? And this will accelerate the usage of the data, the implementation of the product greatly. The same products comes from Oracle, Amazon, and so on and so forth. So there is always a set of technologies that you can pick up, and you need to decide which one is right based on the comparison matrix and reference architectures, okay? And once you got the architecture, for instance, the architect on the product, and do we have architects in the room, actually? Okay, great, so we have one, so I can't blame architects. Okay, Great. So once you got the architecture, you have this like boxes. These are tools, like, and you see how data flows, let's say, from the log files into the tool to aggregate log files, into the Hadoop, into some BI tool. Yeah. What's important to verify here is these connections between tools. And the question you need to ask your big data people or data engineering people is, will throughput between these two tools be enough and sufficient to actually let it go? Because you know the like productivity performance of the system is the performance of the weakest element of this chain. So we need to ask questions like, if we will get like 1,000 messages here, will Flume be able to produce 1,000 as well? Will then HDFS be able to like accommodate this velocity, and so on and so forth, right? This is like very simple but very efficient question, which will be able to help you to validate if tool is right or not. Because what? Because we are working with data, we need to ensure that data goes through the system smoothly, right? And that's the point. Again, checklist, you can either take pictures or we'll be sending the presentation, so it's not like necessary, it's up to you. So the checklist is very easy. There are reference architectures you can use as like a baseline, as a starting point, and then you can see what tools are like proposed in this reference architecture, get the comparison matrix, and decide which tool is most appropriate for you. Okay? Great. Moving on. RDBMS versus NoSQL. Who worked with NoSQL before? Okay. And probably knows the concept, but for those who don't know the difference, so what's the major difference with, like, between RDBMS and NoSQL? Can anybody? Schema flexibility. Okay. Any other differences? Scale out. Yeah. Else? Sorry. Yeah, so basically like tons of differences, yeah? But the major difference and which we keep facing in our projects is that people who used to work with RDBMS, they are comfortable with so-called schemas. Let me show you the, no, hold on, it's a different, sorry. So yeah, so basically, RDBMS are very good when you work with the structured data. For instance, like transactional data, bank like data, like financial data. It's all very structured, yeah? Putting this data in NoSQL can give you some benefit, but in most cases it will not. And these days, what I see in our project is customers are demanding big data. Like, can we put in Cassandra, please? Can we install Hadoop cluster? I'm like, guys, you have perfectly structured data. The size is relatively small. It's like 1 gigabyte of data, let's say, yeah? So why do you need to use these shiny technologies for your project if it's perfectly well works in MySQL, in IBM DB2, in Oracle? Keep using it. There is nothing wrong with these tools, right? So NoSQL is very, very good when you have unstructured data, or like when schema is evolving constantly. For instance, when you don't know what data will come to your system tomorrow. It might have new attributes, right? When you have RDBMS, you will have to change the schema constantly. In NoSQL world, it will change automatically for you. So, and there is like very good comparison metrics from DataStax, the URL here. You can read about the differences. But the whole point is, again, it's not always black and white. So people, the big problem I face is that people either want to go with big data or RDBMS. I'm like, guys, can we combine them? And like, whoa, wait a minute, how we can combine them? Like, okay, you have a data which comes to system very fast, like let's say couple gigabytes per second. So traditional RDBMS like Oracle DB2, they will not be able to cope with this velocity because of transaction like system, yeah? But NoSQL database like Cassandra, for instance, will easily accommodate this load. But the problem, what's the problem with Cassandra if you want to run some SQL queries on top of it? Who can tell? Okay, so the problem with Cassandra is that it is like schemaless. Like there is no even mechanism to join two tables in Cassandra. You will have to read two tables in your application and then combine them somehow. So how can you run some analytics queries on top of Cassandra? Like almost impossible to run them, right? So that's why don't you put data initially in Cassandra, because you have to put it quickly. And then during the night hours, you will transfer it into some data warehouse, RDMS data warehouse, let's say Oracle DB2, right? And then you can run in the morning analytics queries on top of the traditional RDMS using the same SQL queries, and it's like hybrid model, yeah? You can combine these tools easily. And this is the question which data science person should ask. Like, why do we use NoSQL here? Do we really need to use it? Can we use combination of both? Like, and so on and so forth. I will go further because we have some limitation on time, but you will be able to read this like presentation later for more details. So the checklist again is very easy. Use the right approach when it's required. There are like something in between always. NoSQL data modeling. So this is like very interesting. I will just go to the example. So this is like a very simple schema. We have people, we have address where the person lives, we have like a table of cities and the states to which the city belongs, right? Very simple schema, yeah? Who in the room ever created a table in SQL? Like create table, blah, blah, blah. Great, you will understand, it's cool. So this is like, what's good about the relational schema? What's the main benefit of like third normal form on the screen? Huh? Consistency? Exactly. So basically, the main great thing about it is that you create schema once, and then any new query will probably work perfectly with it, right? So I have 3 queries. I want to see the people who live in the specific state. This schema will work perfectly, right? I have queries to check who lives at specific address, at specific state, right, at specific city. Every single query will work fine. Plus, if I will decide to see who lives in a specific city with a name of blah, 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 the same schema will perfectly work, right? What happens in NoSQL world? In NoSQL, the mindset is totally different. In NoSQL, the main thing is that we sacrifice a schema for the sake of performance. So let's say we take all the data and we say, listen, we have like 100 zettabytes of data, right? If you put it into relational database, then if you will decide to see everyone from the city of Austin, it will take like ages for this table to be full scanned and results to be retrieved, right? So what happens in NoSQL is that we tell, listen, if we know that we will be querying by city, right? What if we will split the data by cities? So let's say all the data related to the Austin will sit in one file, let's say, in one piece of data, right? Everyone who lives in New York will sit in another piece of data. And what happens next time when I run the query? Cluster knows where this Austin data located. It goes to this file and just copies this data out to my system. It works perfectly, immediately, right? But what implication of it? The implication is that if I will decide to see who lives in specific state, right, using the same table, the system has to go through each of the file which related to this state, and the performance will be much worse, right? So instead of that, in NoSQL world, what we do is we create another table, this one, where we group data by states, and then every single record which related to Texas will live in another file, right? And when we will decide to do the query by state, we will get this file, throw it out immediately, right? But the problem here, well, not a problem, just like how it works, is that we duplicate the data a little bit, yeah? And this is the main concept of NoSQL. So we say storage is cheap, right? Write operation in NoSQL are cheap and fast, right? So why don't we duplicate the data for the sake of reads? And this is the story. And if you will decide to add the query for, you will have to create another table and another table and another table. And sometimes we have systems which has like 50 copies of the same data. And when traditional people with RDMS might set seeds, it was like, oh my God, it's nightmare. But for the NoSQL, it's the only way to go further, okay? Questions? Is it clear? Okay, yeah? Yeah, correct. So the implication of this approach is that in your application, you will have to do 50 inserts. Like if I add the records, I insert it 50 times in 50 different tables. And yeah, and I have to live with it. But at the same time, I get a millisecond read latency instead of like hours, right? And this is how it works in NoSQL world. Okay, so the checklist, we will skip it. The next very interesting topic is on-premise versus cloud, right? Again, these days, many people go to the cloud. Like, who worked with cloud? Like Amazon, Azure. Okay, cool. So the question is the same. Do we really need cloud? Yeah, and as a data science, when somebody comes to me, I say, oh, okay, we hosted our system in Amazon already. I'm like, okay, did you ask me? Do I want it? And yeah, so the story is that on-premise is still the case. Why? Like, for instance, if as a data scientist, one of the requirements to the system would be that I want to get like couple petabytes of data and then process it, then how much time it will take to get this data from Amazon? Probably a lot, yeah? So the on-premise is still very good for the system which operates on tons of data in real time, let's say, and which has some sensitive data, because like government is not very good with hosting data in clouds. Better velocity, existing hardware. So for instance, if you have tons of hardware, why do you need to go to the cloud if you still can host it like on premise? At the same time, cloud gives the better flexibility, and you probably know all these benefits. But one of my favorite is that the scalability is perfect. Like, for instance, if you will decide to scale your system by 100 machines from 10 machines, you can do it in cloud much faster than on premise, right? And again, the same happens to me. Customers comes and asks, like, do we need to host on premise or in cloud? And nobody like asks a question, can I do something in between, right? And this is the question people need to ask. Like, why don't you put, like, let's say, sensitive data on premise, or data you need to have the best performance access on premise, and then some of the less important data, like some of the historical data, maybe in cloud? Why not? So this is still a very good approach. So again, ask the question, do we really need to go to cloud? And if you don't have a good choice, if you have like requirements in both cloud and on premise, do something in between. There is nothing wrong with having data spread it across. Like, we all spread it around the world. Scalability and performance. This is actually a very interesting topic. So about like maybe 10 years ago, like let's say 20 years ago, everything, like the system used to host on one machine. There was one cluster. It has web server. It had database. It had, I don't know, some ETL. And sysadmin used to play some game, Doom, on it, like on lunchtime, right? It was one machine. And you're laughing, but I had a story when like our system were performing at certain time purely, like no response at all. And we like, we tried to debug it, we tried to see the log files, nothing in there. And then I came to the sysadmin asking, what happens? And he's like doing Alt-Tab, and he have Doom 3 on his screen, like, are you kidding? You playing this like very demanding game on our database server? He's like, yes, thank you. So this is what used to happen. And then people saw this and decided that we need some dedicated clusters, dedicated servers. And they start putting like storage on one cluster, 3 machines, some like processing on another cluster, some analysis on another cluster. But what's bad about this approach these days? What's wrong with it? There is a hint on the right side. Resource management, yeah. So so imagine that you have some nightly byte job, right? Which copies data from one source to another. The cluster which hosts the data is very busy during the night hours, and it doesn't nothing during the day, right? The same thing happens to the processing system. It is busy during the morning hours to process all this data, and then BI cluster is busy during the day once people run the queries. So why don't you combine this computation and put it into let's say, one cluster, yeah, to share resources, because this way, resources which are idle during night hours can be fully utilized for ETL jobs, right? While the resources which were idle during morning hours can be fully utilized for processing data. And during the day, you get better BI, better responsiveness, right? So this is the latest trends in the big data world, to combine everything again into one cluster. But don't allow the sysadmin to play games anymore on these machines, please. Keep them away. So, and the same happens here. As a data scientist, ask a question: why do we put everything on separate like cluster? Why don't we put them on the one machine? And the magic things happens when we host data on the one, like the same machines. So data locality. Who knows what's data locality? Great. So imagine, for those who don't know, imagine that you have data storage and data processing to the same machine. What's good about it? We can, instead of copying data over network, you can get it from the local machine, and the processing goes faster and faster and faster. Yeah. Okay. We can probably skip it. Skip it, because we don't have too much time. Storage. This is my favorite. Netflix. Who knows Netflix? It's like American company who pretty small company. Yeah, people knows it. Okay, great. So the story about the Netflix. They have 25 petabytes of data in like at the end of last year. And the story about this system is that they read 10% of this data daily and write 10% back, which means that they get this data, do some processing, some like data enhancements, whatever, and put data back, yeah, daily, which is pretty much 2.5 petabytes of data, which is pretty significant, right? They have pretty solid amount of events daily, and 350 active platform users who are mostly data science engineers. So these are like data scientists, they pretty much similar to artists, right? So when artists draw the paint, yeah, and somebody complains saying, like, what's this? Like, he's like, I'm an artist, this is my vision. This is how I see the world, yeah? Whatever been drawn then. But the story about the data scientists is that they're pretty much the same. And data scientists, they like to use the tools they're comfortable with, right? If they're comfortable with using Python, they can use Python, right? If they're using Scala, they use Scala, right? And Java, whatever, they can use whatever they want. And Netflix is actually the company which realized that people will be using different systems. And when you decide what will be your storage, this is very crucial decision, like where will I host all my data? So if you will decide to put it into like, I don't know, Windows machine, into the C drive, let's say, then probably not all of the tools which data scientists will want to use will be able to get this data from this C drive, right? Because some of these tools can't just read data from the file system, yeah? And the same problem happened to the Netflix, actually. And that's why they decided to put the data to very universal storage called S3. Who knows what's S3? Okay, great. So, and what they did is they told, okay, listen, guys, 350 data scientists. We put this data to the S3, and every single tool can work with S3, right? Have a connector, have an adapter, you can use it from any system. And this was the perfect decision, and I will tell you why. So this is 2013. This is the architecture of the Netflix. You can see some Hadoop cluster, some Python scripts, and it all gets data from the Amazon, right? What happens in 2014? They decided to actually migrate to some of the new tools, like called Presto. They're using some additional tools for data analysis, and it still sits in S3, right? The architecture on the right side changed significantly, but the storage is the same. What happens in 2015? They add even more tools, and I guess they just decided that they want to use every tool from this 500 I showed you before. This is the aim towards 2050. This is the year when you predicted that AI will replace the humanity, yeah? So, but the storage is the same. And imagine if back in 2013 they will make a decision to host it in Hadoop, right? Then in 2014 or 15 they will have to migrate and migrate and migrate and migrate. So that's why decision about the storage is very important. And as a data scientist, when you've been given this architecture, ask a question if it's the right storage or not. Will we change our architecture? Of course we will, like Netflix does. So again, skipping the checklist, just mention it. And we're coming to deployment. This is probably one of the latest, yeah. So deployment is the way how we deploy our product somewhere. So we have developer, he write the code. We have ETL engineer who gets the data from different sources. We have data scientist who create data model in our language, which process this data. And then we need to combine it all and send to the magic place, which is called production, right? And the way how you actually gather all of these elements and send to the production is called deployment, right? And if it is a manual process, can you please, I will go back, imagine deploying all of these tools, getting all the connection between them, making it all work manually? How much time it will take, like Netflix, to do this? Like probably a lot. And what if next, like for instance, they deployed development cluster, like, and like they start deploying QA cluster. In half a year they finish this process, but for some reason there was so many steps, and this new cluster is different to the previous one because they did it manually and somebody did it like differently this time, and all the new next environment is not the same as previous one. And what happens? You develop something in development environment, in QA it doesn't work, in production it doesn't work at all. So manual work during deployment is prohibited in our project, and that's why we automate it to the 100%. So there should be a magic script, magic button, whatever, which you press, it gathers everything you did so far and send it to production or to the new environment, right? And you can get QA environment in a blink of an eye, yeah? Very fast. And just to give you a couple of keywords in deployment process, because this will allow you to talk at the same language with your DevOps, sysadmin, like configuration manager, and so on. So bootstrapping is actually a process of creating virtual machines. We just create some infrastructure, there is nothing yet there. Provisioning is the process of putting all the software we need on top of it, yeah? Configuration is actually filling it with the proper parameters and initial set of data. Let's say if it's QA environment, we need to put some test data on top of it, yeah? And validation, of course, like people forget about this step, but it also can be automated. We can run set of, I don't know, verification scripts, which verifies data, verify cluster, verify parameters, and you get the valid cluster the same as all the previous ones, and it all works like a charm. So a couple of, again, you don't have to know all the tools, but a couple of the names, like most rock solid these days. So for the bootstrapping, for creating virtual machines, the good tool to use is Terraform from HashiCorp, the same company which created Vagrant. The good tools for provision configuration are Ansible scripts. These days, you will find tons of Ansible scripts on the internet. These are analogs of Puppet and Chef, and so on and so forth. You can see it later. And according to our studies, and we do studies actually, during the automation of deployment, it saves about 90%, up to 90% of time of manual work, which you can spend on something more important. And you can get equal clusters much faster. Everything is good. So the final checklist, we're coming to the final stage. Imagine you got this magic architecture. It is fully deployed using automation. It's all good. You need to do the final check. So imagine this data scientist who is sitting like, okay, let's check if it's good, if it is a good cluster or not. So the last thing you need to check is amount of memory, because in most cases everything is done perfectly, but sysadmins, project managers, they're quite greedy people. They are not like, why do we need 1 terabyte of RAM on this machine? No, 100 gigabyte is enough, okay. And big data, data science is very memory demanding. So even if you will just go and check if memory is okay, you will fix 99% of problems with data, with calculations, with everything. So this is just like last suggestions. So final checklist, you now have some idea about how this whole things works together, and you now have some, keywords, some argumentation like which you can use to talk with your big like data people, with data engineers, and yeah. So in one of the in one of the books I read recently, it was a book about the project management, and the author says that we studied so many different approaches and so on and so forth. And somebody asked him, okay, so what's your the biggest suggestion before people start the project? And he said, the only suggestion I give to people when they start the project isn't doing it like this. Good luck. Okay, that's it. If you want to get any help, any suggestion from my side, feel free to email me. I'm very helpful in answering your questions, guys. And thank you. This was it.
Good. We have questions already for Valentyn.
Okay.
Hi. Thank you very much. I have two questions.
Sure.
One is about the storage of links. Just can you go back to the slides?
To the slides of Netflix, yeah?
Yeah, the storage.
Sure. Which year you prefer?
The last one. The
last one. Okay, yeah. This is my favorite.
Here, you call it the storage architecture, but I see only the S3 and the Hadoop is about the storage. So the rest is just different tools for, for Spark is for ETL, machine learning. The Druid is for another ETL. Presto also, and Hive, simply as secure engine. So why not call it like a data science stack or data processing stack? Mm-hmm. Another question in the back.
Why it is in a storage architecture, yeah?
Yeah, why call it
I have a question too. Why didn't you raise a hand when I asked who worked with Hadoop?
Sorry?
You definitely know what is Hadoop. You never raised the hand when I asked who worked with Hadoop.
Because I know everything you talk about.
It's fine, I'm joking. Okay, yeah, so basically, can you see these two dots between them? So it's like Netflix storage architecture, but yeah, you're right, this is the architecture of the whole system. The whole point was about that this greatly influenced the whole infrastructure as well.
Yeah, okay, but it's very inspiring, thank you. And also, you call you're using the Lambda several times in your slides.
Yeah.
If I understand it correctly, if I'm wrong, please correct me. The lambda is like a particular term used by people when they say lambda architecture. They mean the platform can doing streaming data processing and batch data processing, which means currently is Spark and Flink. So here you're using lambda. I mean hybrid.
Yeah, this is a very good point. I skipped it for the sake of time, but if I will be able to find it in a second. Yeah, this is it. So Lambda architecture, for those who don't know, right, who are not familiar with Lambda. So there are two types of load in a system. Like one is batch load, when, for instance, every night we grab data from every remote server, put it into the centralized data warehouse, and it takes a lot of time, right? The another type of load is more OLTP, real time, when transaction happens, and we need to know if any fraud happened, for instance. We need to know immediately. We don't have a time to wait till the next morning, right? And the whole point about Lambda is that we are not able to process data fast if the amount of data is too big. And if we need to make some decision on top of data immediately, we need to limit this data and put it through the speed layer. Yeah, let's say only important credit card transactions go to the speed layer. But the rest of the data, and there is a typo here, it's batch layer. Sorry, terrible mistake. But there are certain point of truth in this typo. But anyway, yeah. But the rest of the data, which we use in retrospective analysis, it goes through the batch layer, and we combine this like approaches. But the reason why I skipped it very fast like this, the reason under it is that these days there is a new school. Lambda was a new school, and now we have a new school, which says, okay, Lambda architecture, and they look at you and like say, why can't you make your batch layer as fast as a speed layer and keep only one layer? And like, Okay, so now there are people who believes that we can make only one layer which will be equally efficient for both like real-time and batch processing. Okay, does it answer the question?
Yes, thank you
Okay.
very much.
Any other questions before go to the beer? I like IPA. Okay.
Hi there, thank you for the presentation. You referenced like virtual machines quite a lot in terms of the stack.
Sure.
Our business is moving to containers.
Mm-hmm.
What's your kind of experience with like data science and containers and orchestration, deployment and production?
Right. So for the containers again, you make a challenge to me to scroll through this. So basically, what happens? Remember we were talking about putting all the like services into one cluster, like which shares all the resources. The idea is that imagine that you have 3 machines, and like these 3 machines are having like network port, like let's say 3000, yeah. And it happens sometimes that the application needs to use the same port called 3000, right? And if you put all these tools into one cluster, then there might be some concurrency for this network port, for whatever, for some file names, whatever. And this is where containers like Docker helps a lot. You can imagine container as a virtual machine inside, let's say, virtual machine. So you have physical server or virtual machine, and Docker is, again, small machines inside this machine. Okay, so it's like another level of virtualization, let's say, which is called soft virtualization. Okay, so and for data scientists, it's just like another tool in the cluster which allows you to have better granularity inside the virtual machine, to fix the concurrency for the resources, for the port numbers, and so on and so forth. Okay.
Thank you.
If people are interested in Docker, I can get a Docker person along one day. Is that something? Yeah, I thought. Yeah, it's come up a few times.
This is a great topic.
I will go and seek out a Docker expert for a future meeting. Any other questions? No, Valentyn, thank you so much. That was absolutely superb.
Thank you, guys.
Okay.
Thank you.
So if you filled your